All right, folks. Welcome back. Hopefully, the weekend was a good one. Come back rested. Okay. What we're going to see here today is I'm going to talk you through some types of waves, some wave speed, and then sound is. Yeah. Um, Sound and waves unit, kind of an interesting one. It'll be a little trickier to do some labs with you, but we're going to give it a shot nonetheless. Okay. You got a quiz on Friday. That one will again be open note, and I'll explain that as we get closer to it. You're also going to have a test next Friday, um, unless we run out of things to talk about. Then we'll figure that out. Okay. So here we go. All right. Um, so there are two types of waves. Okay. So what we're going to see here is there's a transverse wave, and then there is a longitudinal wave. Okay. Now, take some time and go ahead and look at the parts of these. Right? Make sure you write those down. Make sure you draw these up because this is going to be a part of your homework stuff, and this will be something that we'll look at also later on. All right. Transverse wave. Transverse wave is an up and down. It's an old school sine or cosine wave that we've seen. All right. It's got a crest, which is the high point. It's got a trough, which is the low point. The wavelength on this one, how much one wave would be from the crest to the crest, the beginning of the crest, the beginning of the crest, the trough to the next trough. It's basically same point, same point. Do not think that it is from the crest to the trough. That's only half a wavelength. You need at least you need two of this. You need to get to the same spot again. Okay? Over on the other side, what we see here is we see that we've got a longitudinal wave. Okay? Longitudinal wave, it has an area of compression and an area of rarefaction. Right? Compression is obviously going to be where the squeeze of those molecules happen. Rarefaction is going to be where there is a space between the molecules. So there really is a lot of nothing in that spot there. Okay? So transverse looks like that. You can see the up and the down. Anyway, for us, longitudinal, it appears as if everything's the same, and then all of a sudden, what you see is you see that wave going through it in the form of basically that those molecules getting tighter. So sound is a longitudinal wave. So when we see sound, those areas of compression are what are going to be the things that come to you and go into your ear and um, then go through the psychology of your ear and everything like that, or sorry, through the anatomy of your ear and make those kind of compressions something that we can then understand. All right. Um, I remember very vividly finding out that sound had compressive properties when I was about 11 or 12. And my buddy and I, and you know how much I don't like that shit, right? I absolutely despise it. But my buddy and I, what we did was he got his hands on some M80s. M80s were an eighth of a stick of dynamite. The beautiful thing about these M80s were they had waterproof fuses, right? Probably highly illegal, but the statute of limitations I think has passed, so I can share this story with you for that, not have any repercussions on that one. But basically, what we did was we took rubber bands, put them into or tied them to a rock, lit them, tossed them into a local creek that was there. Thankfully, the creek was relatively deep because when these things went off, they made a pretty good amount of noise. And underwater, that concussive force was meant to knock fish unconscious. um, but thankfully, probably for my own sanity, there were no fish in that creek at all, and all it did was just make kind of a nice little splash for us, and we kind of giggled about it and everything like that. Okay. Um, but what you can see in the top right corner here is that we can kind of parlay this or make this look like a transverse wave um, by basically just taking those compressions, turning them into crests, the rarefaction, the area where you're rarely going to find a sound or a wave, and turning those into troughs as well. Okay. Um, so again here, just a nice little image. If you've ever been to the Science Museum in St. Paul, the wave generator that they have there, kind of in the main atrium area, similar to this. And what you're going to see here is that by compressing the air, by causing this expansion and then contraction afterwards, what you do get is you do get this sound wave. All right. My vocal cords are currently vibrating enough for you so that what you can hear is you can hear that sound. My tongue, my mouth, my teeth, lips, everything like that is then trying to turn it into something coherent that your brain can analyze and say, okay, that's the English language. I can understand that. So the compressions are the actual sounds that you are hearing. The rarefactions are the moments in between. Um, so they're that kind of bit of silence, like right there. Yeah, that would be a rarefaction. You're rarely going to find a compressional wave there. Okay. Um, so calculating wave speed using frequency and wavelength. So frequency is measured in hertz. That's waves per second. I know, again, it's been a bit since we've seen that one. Um, Wavelength, that's going to be lambda. I know it looks like a weird symbol, backwards, upside down Y, backwards H. That's going to be measured in meters, and our velocity is going to be meters per second. Hertz is basically just how many oscillations or how many waves are happening in that second or per second. Okay. The way that I'll mess with you, I can change wavelength to kilometers or millimeters. Likely it'll stay as meters, but at least in the interim here. But be aware, we will see that as a possible way to kind of mess with you and change stuff. All right. Formula looks like this: V equals F lambda. So our velocity or our wave speed is equal to the frequency times wavelength. All right. Couple conceptual or a couple questions for you here. What happens to the wavelength of a 440 hertz acoustic wave when it enters a steel railroad track from air at 20 degrees Celsius? Um, so speed of sound in different medium. Now, because we're again talking about um, that speed of sound and how it is a compression wave, that allows us now to look at this and really start to see that if the molecules are closer, meaning like lead, copper, glass, steel, versus water, mercury, ethanol, chloroform, versus helium, air, and all that stuff, then we see that the sound wave can travel significantly faster, right? If you go out into the void of space, where there is no air and no way for us to transfer the sound wave, if you were able to survive the lack of oxygen and also the 2 or 3 Kelvin temperature out there, the ability to talk there would be impossible just because there's nothing for your vocal cords or your sound to compress. So in the vacuum of space, there isn't any really sound, so to speak. Um, the way you would have to do that is through radio waves or microwaves or stuff like that. All right. Anyway, sorry. Um, so in this one, we ask what happens to the speed of the sound of the wave, right? So V increases. So if our velocity increases, then what should happen to our frequency? Meaning that if our velocity increases, our frequency also, for this one, should increase. Does it change the pitch of sound when it goes through it? Um, no, not really. It shouldn't. Okay. And again, the reason is that if you think about it, my wife was a swimmer throughout high school. Um, and the kind of crazy thing for her experience was she swam at sections and she swam at a collegiate pool. And the collegiate pool had underwater speakers. Now, if we're looking at this and we're saying um, that, you know, we should be able to see a change in pitch, a change in how high or how low it is, well, in the water, you don't. Okay? In the water, you're not going to hear that change. What ended up happening with her was the sound was exactly the same, right? And all of that time spent swimming, all of that time spent in the pool doing the lengths and lengths and lengths that she talked about were a lot easier with the music there, right? If you think about your own workout experience, imagine now not being able to have that music. That was helpful for her. Okay? So our frequency doesn't change when the medium changes. Our wavelength will increase though. Okay? So just be aware of that. I know I misspoke earlier. Um, our frequency, that sound, pitch, everything like that, that's going to stay the same. And because of that, what we'll see is that our wavelength should increase. We're just going to get a nice longer wave for ourselves here. Okay? So um, the wavelength there in there will increase by a factor of basically 17.38. Right. So the way that we do that is we take our frequency, the 470 hertz, and we take the speed of sound, and we go ahead and we look at it with that. So the speed of sound in air is 343. All right. We take that 343, and the speed in the steel is almost 6,000. And so what we're able to do is if we wanted to really look at the individual wavelengths of those, we would take the 5960 divided by 440. We would take the 343 divided by 440 as well. Right. Now, there was a physical science text I taught out of at the previous school, and they talked about having your students do an experiment. The experiment was find a local railroad track. Now, please understand, I am not telling you to go do this. This is one of those moments as a teacher where it's like, yes, the reasoning is sound, but the actual purpose for it is stupid, so to speak. All right. They said, I'm going to tell you nonetheless. All right. They said, go to a railroad track, position yourself and your friend so that you're, say, 100 yards apart. Right. Have your friend take out the hammer that they brought with, because who's not carrying a hammer on a daily basis, right? And hit the railroad track as hard as you can. They said what your friend should experience is they should hear through the ear that's on the railroad track faster than through the air. And that compression noise is going to travel through particles that are closer together faster, right? So it should get there quicker. Now, again, the one caveat that they left out was make sure they're in train coming, folks, right? I know, it's crazy, but don't necessarily go and do that one. Okay, take my word for that one. All right. So, sound wave is a three-dimensional wave. And that's a crazy thing, right? It would be great if, as we looked at it, what we were able to say is that this is just two dimensions. It's just going straight at you. All right. But it's a three-dimensional version of a rock being dropped in water, right? If you've ever seen that rock drop, it makes the concentric circles, and they just continue to build and build and build and build, right? Well, that's what sound wave really is. If we just had a tone and a tone and a tone, and just kept that, kind of that same tone over and over again, what would happen is that thing's going to spread out, right? It's going to spread out left and right, up and down, and then fro as well. Okay. So what we end up seeing is that it is three dimensions. As much as we want to say it's just a two-dimensional wave, and we could isolate it and just shoot it straight to you, if you were sitting in class and just be able to say, hey, take a look at this, and that would just go straight to you. Fortunately, we cannot do that. Okay. Example, big old battleship launching shells at something. You can see the sound wave up on the top here, right? It's pretty darn extreme here, pretty darn crazy that thing is blasting out that way. Okay. And then last one. This is an eruption that somebody caught on camera. And what you can start to see towards the end is the actual sound wave going through the clouds. All right. So if you watch this third time, check out the clouds and watch how that sound wave now starts to process and go through those clouds and make clouds right there. All right. The other interesting part is watching it actually on land. and see how this goes down the hill just like it does right there. All right. And maybe some of you have seen the sound waves and stuff like that that are present on like movies or anything like that. Um, so that's kind of it for the day. All right. Um, Hopefully this makes a little bit of sense. I've got a couple, I think 3 or 4 questions on Schoology, or there's a direct link out there too. If it's easier to draw them on paper and share those with me, go for it. That's absolutely fine. If you want to open up the Google Doc and draw them in there and do stuff in there, then that's absolutely fine as well. All right. Hope you folks are doing good. Thinking about you. And take care. All right. We'll see you later.